Isn't it still a bit mind-blowing, though? You just set your phone down and poof, it starts charging. No wires.
It really is. You see it every day, but it still feels a little like, well, like magic.
Exactly. And you've probably, stopped and thought, okay, how is this actually happening? That's exactly what we're going to dive into today.
Yeah, we've got some really interesting sources. Everything from like the super technical PhD level physics breakdown
Uh-huh.
to a really neat explanation designed for like a 5-year-old.
Uh,
And our mission today is kind of navigate between those two extremes.
Right, to really get the core idea. We're not just scratching the surface. We want to unpack the actual electromagnetic stuff that makes this wire-free power happen. Ready to look under the hood.
Absolutely. Let's start with the basics. The real foundation, electromagnetism. And the key concept is electromagnetic induction.
Okay, electromagnetic induction. Sounds
Mhm.
hefty. Simple terms first.
Okay, simplest terms. A changing magnetic field can make electricity flow, and electricity flowing can make a magnetic field.
Ah, okay. Like a two-way street.
Exactly. That back and forth is the secret sauce between the charging pad and your phone. The pad makes a magnetic field, the phone catches it and turns it back into electricity.
Gotcha. So the pad's creating this magnetic vibe and the phone picks it up.
Pretty much. Now, the science behind that is Faraday's law. Basically, it says the faster the magnetic field changes as it passes through, say, a loop of wire, the more electrical force voltage you create in that wire.
So wave a magnet faster near a wire, get more juice.
That's the idea. Now, apply that to the charger and the phone. They both have coils of wire inside.
Right, little spirals of wire.
Yep. The charger sends an alternating current one that flips back and forth really fast through its coil. This makes a magnetic field that's also constantly changing, growing, shrinking, flipping polarity.
Okay.
Some of that changing magnetic field then goes through the coil in your phone. And because it's changing, boom, Faraday's law kicks in, and it induces a voltage in the phone's coil.
And that voltage charges the battery.
You got it. Now, how well this works, how effectively that energy jumps across, is measured by something called mutual inductance. Think of it as how well the two coils are magnetically linked.
Mutual inductance. Like how well they can hear each other's magnetic signals. If they're close and lined up nicely, the signal's stronger.
Perfect analogy. And yes, closeness is huge, but also the size of the coils, how many turns of wire they have. Even the material between them, like your phone case, matters.
Ah, okay. Yeah, a thick case might muffle the signal. Makes sense. So how do we score this connection? Is there a number for it?
There is. It's called the coupling coefficient, usually written as K. It's basically a score from 0 to 1.
0 to 1.
Yeah. 1 means perfect magnetic linkage. Almost all the field from one coil goes through the other. Super efficient. 0 means basically no link at all.
So low K is like shouting across a crowded room. Most of the energy gets lost.
Exactly. And that K value is super important for efficiency. Now, to boost that efficiency, especially when K isn't perfect, we use a clever trick. Resonance. Resonant inductive coupling.
Resonance. You
Wow.
mentioned that, like pushing a kid on a swing, right? Timing it just right.
That's the classic analogy, yeah. Both the charger circuit and the phone circuit are designed using capacitors and those coils to naturally vibrate electrically at the same specific frequency.
Like tuning forks.
Sort of, yeah.
Yeah.
Or like tuning two radios to the exact same station. When they're both tuned to this resonant frequency, energy transfer between them becomes much easier, much more efficient.
So they're vibrating in sync, electromagnetically speaking.
Precisely. And the actual amount of power that gets across depends on that resonant frequency, the mutual inductance, our K factor, and also the electrical resistance in both circuits.
Resistance. Like friction for electricity.
Kind of, yeah. It turns some energy into heat. So to get the most power across, the circuits need to be kind of impedance matching, technically. The phone needs to look like the right kind of load for the charger to deliver power to efficiently.
Okay. They need to be electrically compatible.
Exactly. And efficiency. Well, it's never 100% with wireless.
All right.
You always lose some energy, mainly because that magnetic link, that coupling K, isn't perfect, and because of that resistance in the wires heating things up a bit.
Which is why my phone gets a bit warm sometimes.
That's usually why, yeah. The better the coupling and the lower the resistance, the less energy is wasted as heat and the more efficient it is.
Makes sense. Okay, inside the charging pad.
Huh?
It's plugged into DC from the wall, but you said it makes an alternating field. How does it switch it?
Ah, good question. There's a driver circuit in the charger. Its whole job is to take that steady DC power and chop it up, switch it back and forth extremely quickly to create high-frequency AC.
How fast are we talking?
Really fast. For the key standard, that's the common one, it's typically between 100 and 200 kilohertz, so 100,000 to 200,000 times per second.
Wow.
Yeah. And they use efficient electronic switches, things called H-bridges or Class E amplifiers, to do this switching without wasting too much power themselves.
Okay, rapid switching creates the changing field. But how does the charger even know my phone is there? It doesn't just blast energy out all the time, does it?
No, definitely not. There's communication involved. The key standard is a good example again. The charger periodically sends out little pings, tiny power pulses, just to see if anything responds.
Listening for an echo.
Kind of. If a key-compatible phone is placed on it, the phone detects that ping and responds. Then they start this little digital handshake. The charger can actually change the strength, the amplitude of its signal slightly, that's amplitude modulation, AM, to send coded messages to the phone.
Like Morse code, but with magnetic field strength.
A bit like that, yeah. It can tell the phone how much power it can provide, for instance. And the phone talks back, too.
How does the phone talk back without its own transmitter?
Clever trick. It slightly changes how much power it's drawing from the field. It modulates its own load impedance. The charger is sensitive enough to detect these tiny changes in the power draw, and it interprets them as messages from the phone. So the phone can say, hey, I'm at 80%, or I need more power, or I need less power. It's a constant, silent conversation happening through the magnetic field.
That's seriously smart. A magnetic dialogue.
It really is, and it gets smarter. The system can even tweak the operating frequency slightly, maybe plus or minus 15 kilohertz around that resonant point, to stay tuned perfectly. Even if you nudge the phone a bit, it actively optimizes.
So it's constantly fine-tuning to the best connection.
Mm-hmm.
Amazing. What about the coils themselves, the physical things? Does the shape matter much?
Oh, hugely. Coil design is critical. Usually they're flat, spiral, planar coils. Making them involves trade-offs. More turns of wire generally means more inductance, better magnetic field storage, but it also changes the frequency it wants to resonate at.
Right.
And the overall size, the radius, affects the field strength and how well it couples. Engineers have to balance the number of turns, the wire thickness, the spacing, the diameter, all to hit the target inductance and resonant frequency.
A careful balancing act. What about losses in the wire itself? You mentioned resistance.
Yeah, and at these high frequencies, it gets tricky. There's something called the skin effect. The AC current doesn't like to flow through the middle of the wire. It crowds near the surface, the skin.
Okay. Why does it do that?
It's due to eddy currents induced within the conductor itself, basically. But the result is that the effective area for the current is smaller, so the resistance goes up compared to DC.
Ah, less room for the electricity to flow means more resistance.
Exactly. To fight this, they often use special wire called Litz wire. It's actually made of many, many very thin strands of wire, each individually insulated, and then woven or twisted together in a specific pattern.
Litz wire. Sounds fancy.
It gives the current lots of surface area to flow on, reducing that high-frequency AC resistance, so less energy wasted as heat in the coil itself.
Like a bundle of tiny straws instead of one big one.
That's a decent way to think about it. And we also want to minimize energy just radiating away as radio waves lost to the environment.
Right. Keep the energy focus between the coils.
Yeah, that's helped by keeping the coils close, tight coupling, high K, and by making the resonant circuits have a high Q factor or quality factor. High Q means the circuit stores energy really well at resonance and doesn't dissipate it quickly. Less loss.
Okay, so keep them close, use Litz wire, and make the circuits high Q. Got it.
Oh, yeah.
Now, safety. We're talking electricity, magnetic fields. What keeps this safe?
Very important point. Standards like key mandate multiple safety features. There's overcurrent protection circuits that shut things down if too much power is drawn, like if there's a short circuit or maybe a metal object on the pad.
Ah, foreign object detection.
Exactly. Fuses, too, as a backup. And strict power limits. The early Qi standard was around 5 watts, though newer versions go up to 15 watts or sometimes more, but it's all carefully controlled to prevent overheating.
So it won't just keep pumping power into a coin you left on the charger.
It shouldn't, no. It's designed to detect that and stop or limit power. Plus, there's temperature monitoring, usually, in both the charger and the phone.
Okay. And what about interference? Could my charger mess with my Wi-Fi or Bluetooth?
It's a consideration. They use shielding materials, often ferrite sheets behind the coils, to help contain the magnetic field and direct it upwards towards the phone, reducing stray fields.
Like blinders on a horse.
Kind of, yeah. And the frequencies used, that 100, 200 kilohertz range, are generally in what's called the ISM bands, industrial, scientific, and medical. These are bands set aside for low-power, short-range devices like this, partly to minimize interference with licensed radio communications.
Okay, good. So even with all this clever tech, wireless is often still slower than just plugging in.
Hmm.
What are the main roadblocks?
Well, the biggest ones are still those fundamental limits we talked about. Getting that coupling coefficient K really high, close to 1, is hard in practice with flat coils separated by a phone case. You're usually looking at maybe zero point 0.5 to zero point 0.7 in a good setup.
So still losing a fair bit of potential energy transfer right there.
Yep. And then there are the resistive losses in the coils, even with Litz wire and in the electronics. Plus, alignment is still a big practical issue if you don't put the phone down in just the right spot.
The dreaded wiggle dance.
Exactly. The coupling drops off fast if the coils aren't aligned well, and charging slows way down or stops.
Yeah, that's definitely noticeable. Are things getting better, though? Any advances?
Oh, for sure. One approach is using arrays of coils in the charging pad. Instead of one big coil, you have several smaller overlapping ones. The charger figures out which coil is best aligned with the phone and uses that one, or maybe a combination.
Ah, so it increases the sweet spot, like how some electric toothbrush chargers don't care how you drop the toothbrush on.
Precisely. That often uses a simpler form of induction, sometimes without tight resonance, but multi-coil arrays in phone chargers make precise placement less critical.
Okay, that's cool. Anything else?
There's ongoing work on making the systems more adaptive, using smarter control algorithms, maybe even machine learning, to dynamically adjust frequency, power levels, maybe even which coil to use in real time based on the measured coupling and distance.
So the charger learns the best way to charge this phone in this position right now.
That's the goal. Smarter, more flexible, and hopefully more efficient charging, maybe even over slightly larger distances eventually, though that gets much harder.
Right, the physics gets tougher further away. Okay, we've gone deep into the tech. Can we circle back to that 5-year-old explanation? How do these concepts map?
Let's try. Remember the magic blanket charger and the secret sensor phone? That invisible energy field. That's our electromagnetic field, created by the alternating current,
Okay,
the coils talking to each other. That's mutual inductance and resonance needing to be on the same channel or frequency to communicate well.
got it.
Why the phone has to stay on the blanket, that's the coupling coefficient K dropping off rapidly with distance. The magic doesn't reach far.
Right, weak link if it's too far.
The safety stuff, like not charging a coin, that's the charger being smart enough to know what it's talking to using that communication protocol, and charging maybe being slower than a wire. That's the efficiency loss, some of the magic energy turning into heat because the transfer isn't perfect.
Wow, okay, so the simple analogy actually tracks pretty well with the complex physics, just using different words.
Exactly. It's all the same underlying reality, just described at different levels. It boils down to manipulating electricity and magnetism in very clever, controlled ways based on principles we've understood for, well, over a century.
So we've really covered the spectrum today, huh? From Faraday's law and resonant circuits right down to magic blankets. It's genuinely fascinating how much complex science is hiding in plain sight in these charging pads.
It really is. And the key takeaway, I think, is that this convenience isn't magic at all. It's solid engineering built on a well-understood physics induction, resonance, controlled by smart electronics and communication standards.
Right, that feeling of ease, that it just works feeling, is the result of decades of scientific understanding and really clever engineering refinement. Definitely makes you think. Yeah. Well, if we can do this for phones, using these principles of wireless power transfer, what else? Where else could this technology go? Beyond just charging our gadgets, could we power medical implants, sensors in hard-to-reach places, maybe even vehicles someday?
That's the exciting frontier, isn't it? Scaling this up, making it more efficient over distance, finding new applications is definitely something to ponder.
Absolutely. A great thought to end on. Well, thanks for joining us on this deep dive into the surprisingly complex world of wireless charging.